Hello, learners. This is Mr. Weissert. We're going to be introducing probability today. So let's get started. If you would like to follow along with AP Classroom, you'll find this in Unit 4, Topics 4.1 through 4.3. If you're in the book, The Practice of Statistics, updated 6th edition, you'll find this in Section 5.1. Probability is the long-run chance of something happening. So it's a random process. They're always going to be between 0 and 1. You can't really think of probability without thinking of something being simulated. So we think of things in the long run, not in the short term, because the short term is really unpredictable. But in the long run, if you do something enough, it'll eventually be what the probability should be. So to simulate this, let's just think about free throw shots for a second. Say you're a 50% free throw shooter. Now, if you hit one shot, you either are going to make it or you're going to miss it. So if I just do one shot, hey, I made it. I have hit 100% of my shots. And so right now I'm a 100% free throw shooter. Is that really true? Well, no, because you have to do many, many shots to level that out. So if I do it again, oh, okay, I missed that one. So now I'm at 50%. Well, I'm back up. Now I have 2 out of 3. So we're at 66.7%. And I could keep this going. And what you'll see is a lot of fluctuation at the beginning. And it might go up above that 50%, might be below, but eventually it's going to approach that 50%. You see these numbers here still fluctuate a little bit. So I've taken 50 shots and I'm exactly at 50%, but that's not necessarily going to be the case if you try this. So if I keep simulating this and do 50 more shots, now I'm down to 48. And it keeps going back and forth, but eventually if I do this enough, that's not going to really be much different than 50%. It'll hover a little bit above or below 50%, sure, because it's a random process. But knowing that I'm a 50% free throw shooter, I don't know why that's so hard to say, that's eventually going to level off. So that's what the law of large numbers is. If you do something in the long run, eventually it'll be what the probability stated to be is. Let's model an example. So according to the Book of Odds, the probability that a randomly selected US adult drinks coffee on a given day is 0.56. So I'm a coffee drinker. Let's interpret this probability. And what you would say is, if you take a very, very large random sample of US adults, approximately 56% of them will drink coffee on that day. We don't just say 56% of US adults drink coffee on that day because this is a sample. Okay, so if we have enough people to replicate this, then we can say, yeah, that approximate percent of coffee drinkers will be 56%. That's just a long-term thing. Part B, if a researcher randomly selects 100 US adults, will exactly 56 of them drink coffee on that day? Well, think about the free throws we just took. If I take 100 free throws, was I guaranteed that exactly 50 of those made it? No, not likely. I mean, it's possible. But it's very doubtful. So we would say something like, that's not really likely to happen. If only 100 adults randomly selected, the number that drink coffee on that specific day is likely to differ from 56. Let's do a little check understanding. So we're going to estimate some probabilities. We have 4 different explanations and 6 different probabilities to match them. So what we want to do is we want to take the 4 best choices from there and put them in the probability. And then you should come up with an example that could mimic that probability based off the number. So we're going to use the first one. This outcome is impossible. It can never occur. Out of these 6 choices, which one is the best one? Well, that's going to be 0. What about if the outcome is certain? It's going to occur on every trial. Guaranteed. Well, that's 1. That's 100%. This outcome is very unlikely. Could happen, but it's not going to happen very often. It'll occur once in a great while in a long sequence of trials. Well, we have 0.001 and 0.3. Out of those descriptions, we're going to say it's 0.001, very unlikely. And then the last one, this outcome will occur more often than not, but doesn't occur almost every time. Well, more often than not would be more than 50%, but doesn't occur almost every time. That means that 0.99 probably isn't going to make it there. So 0.6 would be the better option. Think of some examples that you could use to come up with that. What is something that is impossible to happen? Well, I said rolling on one 6-sided die and getting a 7. Well, that's impossible because the die are labeled 1 to 6, so you're not going to get a 7. Can you think of any others? What about a 100% chance of happening? Well, going back to the die, you could say rolling a six-sided die and getting a number 1 through 6. Guaranteed to get one of those, unless it lands on a corner or something, but we're going to neglect that. The third one, the outcome is very unlikely, but will occur once in a while in a long sequence of trials. Think about drawing a number out of 1,000, right? 0.001 is 1,000th. So if I randomly select a number and expect the number 8 to come up, 0.001 would be that probability. And the last one, I'm doing the same kind of thing with numbers. Again, you can do any sort of scenario that works. The likelihood of selecting a number less than 7 from a list of numbers 1 through 10. So 1, 2, 3, 4, 5, 6, 6 out of 10. Can you think of other ways to describe the remaining probabilities, 0.3 and 0.99? I'll let you think of that on your own. Let's do another example. In the Wheel of Fortune, Pat Sajak is no longer the host, by the way. I think it's Ryan Seacrest. There is a 1 in 9 chance, 11.1% probability of spinning bankrupt. So if you look at the bankrupt, that's going to occur about 11.1% of the time in this wheel. We want to interpret this probability. So think about probability as a long run chance. It's not if I do one spin, it has an 11.1% chance of landing on bankrupt. That is true. That's not how we interpret it. Interpretation is going to be something like if we were to do this spin many, many, many times, we're going to land on that bankrupt approximately 11.1% of those spins. So remember, probability is a long run process, a long run chance process. Number 3, in 9 consecutive spins of Wheel of Fortune, none of the spins land on bankrupt. The next contestant worries that he's more likely to land on bankrupt now because bankrupt is due. Why is this wrong? Well, every spin, is independent. So it's not like one spin's going to affect the other. So the wheel's got no memory. So I say something like the wheel has no memory. The likelihood of getting bankrupt is always going to be 11.1% any spin you make. So there's no real streak situation here. It's sometimes you end up getting a bunch of bankrupts in a row or not getting a bunch of bankrupts in a row because of the random process. But over many, many spins, you'll get 11.1% of those spins to be about a bankrupt. So the likelihood of getting bankrupt is 11.1% for each spin. It's like flipping a coin. The likelihood of getting heads or tails is going to be 50%, no matter how many times you get heads in a row. All right, so let's talk about simulating. We're going to try to mimic that random process, and we're going to do 3 things with a simulation. First thing, we're going to describe how to use that random process to perform one trial. Okay. Then we're going to record the results of that trial. We're going to do many of those trials, put it together in a dot plot usually, and then we're going to answer the question of interest. So there's always going to be a question. Based on our simulation, we'll answer that question. So we do one trial, then we do many, many trials, and then we answer a question. So how does that look? In an attempt to increase sales, a breakfast cereal company decides to offer a promotion. Each box of cereal will contain a collectible comic book featuring a popular superhero. Man, I miss cereal boxes with stuff in it. The Flash, Batman, Superman, Wonder Woman, or Green Lantern are our superheroes. The company claims that 5 of the comic books are equally likely to appear in each box of cereal. A superfan decides to keep buying boxes of the cereal until one day they have all 5 superhero comic books. The fan is surprised when it takes 23 boxes to get a full set of comics. Here's our question. Does the outcome provide convincing evidence against the company's claim that the 5 comic books are equally likely to appear in each box of cereal? So again, the fan, it took 23 boxes. That's a lot of boxes to get all 5 superheroes. You'd think if they were more equally spread out, you would get them in maybe 5 or maybe a little bit more than 5 boxes. But in this case, it took 23. So to help answer if this is unlikely to happen, so we can see if the game is rigged, we're going to do a simulation. So how would we use a random number generator to perform one trial of this? Now, the key thing about this simulation is we're gonna stop the process until we get all 5 comic books. So in order to do this, you got to think about how we're going to do this. We got 5 different comic books. We're going to use a random number generator. So we're going to have to number those 1 to 5. So I always assign a superhero a number. So let's say the Flash is 1, Batman is 2, 3 is Superman, 4 is Wonder Woman, and 5 is Green Lantern. Now that you got a number assigned, we'll have to do some sort of random process. Well, in this case here, we got to keep selecting a number. We can do repeats. In fact, we should do repeats because sometimes the number 1 or number 2 or 3, 4, 5 are going to come up multiple times. So we're going to pick a random integer from 1 to 5 to simulate buying one box and looking at which comic book you get. Now, we're going to have to do this until we get all 5. So we keep generating random integers from 1 to 5 until all 5 numbers appear. Now you're going to stop when you see all 5, but then we're going to have to figure out how many comic books we ended up getting. Let me show you on the calculator how you can do that. So what you'll do, let's say if you random number generator on your calculator, you'll hit the math button if this is a TI-84, and you'll go to prob, and this is just rand int. We're not going to do no repeat because we're going to get the same number over and over again. And we're going to do lower as 1, upper as 5, and we're just going to select 1. And the goal is to just keep selecting it until you get all 5 numbers. So I'm going to press enter again, and my first one was a 5. Now I'm going to keep pressing enter until I get all 5 numbers represented. So count with me. That's 1, 2, oh, I got a 5 again. So 3, oh, there's 1, 4, 3. So I need 2 and 4. 5, well, 3 again. 6, oh, there's 4. 7, well, 1 again. I need 2. 8. So it took me 8 tries to get all 5 numbers. Well, that's pretty good. And what I would do is I would keep repeating that process and eventually do many of these. So I could do like 100 of these simulations and see, all right, how many of those 100 are going to take 23 or more boxes to get? So let's go back to the problem. Here's a simulation, okay? So remember, when I picked a number, I picked 8. Looks like 8's a pretty common number, right? So I'm doing pretty good. But in this little trial where the guy got 23 boxes, that's pretty out there. It's pretty unlikely to get 23. Look at, that's 22, so that's 20. So 23 would be here, and I'm not seeing any, and then definitely only 3 that got above it. So let's look at what the data 18 represents. One trial where it took 18 boxes to get all 5 superheroes. So that just represents one simulated random number generator, and we stopped when we got all 5 superhero comic books, and it turns out it took 18 trials to get that. Now, let's use our simulation. We got 100 trials in this dot plot of the simulation, and let's look at the probability of getting 23 or more. We always go in the more extreme direction to get a full set. Now, how many of those were 23 or more? Well, it looks like these 3 here. And since there are 100 of it, 3 out of 100, so 3%. That's pretty unlikely. That's pretty small. Now, let's look at the question. Based on the results of our simulation, is there convincing evidence that the 5 superhero comic books are not equally likely to appear in each box? Explain your reasoning. Now, anytime you have a small percentage in your simulation, we're gonna find convincing evidence. So in this case here, because it's fairly unlikely, less than 5%, that it's going to take 23 or more boxes to get a full set of by random chance, assuming that the game's not rigged, assuming it's equally likely to select any superhero. We have convincing evidence that the books are not equally likely to appear. In other words, the game is rigged, guys. Maybe some superheroes occur more often than others, but in our case here, this is pretty sus. Hey, slang. All right, next question. At a local high school, 95 students have permission to park on campus. Each month, the student council holds a golden ticket parking lottery at the school assembly. The 2 lucky winners are given reserved parking spots next to the school's main entrance. Last month, the winning tickets were drawn by a student council member from the AP Statistics class. When both golden tickets went to members of that same class, some people thought the lottery had been rigged. Is that the case here? There are 28 students in the AP Stats class. 28. There's 95 that can park. So you guys are pretty lucky. 28 out of those 95 are in AP Stats. Lucky. all of whom are eligible to park on campus. We want to perform a simulation to estimate the probability that a fair lottery would result in 2 winners from the AP Stats class. Now, I can show you how to get that theoretically, but for right now, let's talk about doing a simulation. How would you use a random table of random digits to carry out the simulation? Now, before I actually explain that, let me just go through giving you a line from the table of random digits. Remember, we did this back in the sampling lesson. So I'm going to actually skip to part B for a second. So we're asked to perform 3 trials of the simulation using the random digits given. Make your procedure clear so that someone can follow what you did. In our simulation, what we're trying to do is we're trying to simulate drawing 2 lottery ticket winners and seeing how many of those, or seeing how many, after a certain amount of trials, how many times both of them were AP Stats students. So I'm going to do a trial here. So what we're going to do is we're going to select that 70 because that is a number between 1 and 95. All right, so 70 is good. That next number was 70, but that's a repeat, so we're going to cross that out because we're not going to draw the same person twice for a lottery. And the third number was an 84. Again, that's between 1 and 95, so we're good. And both of those numbers are above 28, so we would consider those to not be AP Stat students. So in that one trial, none of them were AP Stat students. In the next one, I see a 10, and I see a number, I think that's 98. Let me go back here. Yep, 98. 98's too high. 95 is our cap. And then there's a 55. Now, out of those 3 numbers, 10 is between 0 and 20, or 1 and 28, so that's an AP Stat student, but it's not both of them. And then the third trial, I got 18 and 19. Both of those were AP Stat students. So out of my 3 trials, it looks like one of those had a situation where both were from the AP Stats class. So it's not too bad. Let's go back and let's talk about the process we just did, and we'll write that in our notes. So how would I describe what I just did? Well, I'm going to label all the students in the AP Stats 0, 1 to 28. Careful with this 0 there. You got to have the same number of digits. So we don't want to just say 1. We got to say 0, 1. We're going to label the remaining students that have permission to park from 29 to 95, since there are 95 students total that have permission to park on campus. We're going to skip over the numbers 96, 97, 98, 99, and 0, 0. So if you come across those numbers, just X amount, we won't use them. We're going to move left to right. We're going to look at pairs of digits until we come across 2 different pairs from 0, 1 to 95. And the 2 students that correspond to these numbers are going to win the prize. Record whether both students were from AP Stats and repeat this process many, many times. So generally in a simulation, you want to do at least 50, preferably 100 or more if possible, but it's very time consuming to do these without technology. Here are the results of a large simulation. So in 9 out of the 100 trials, both golden tickets were won by the members of AP Stats class. Do these results give convincing evidence that the lottery was rigged, that the lottery was not carried out fairly? Explain your reasoning. Well, 9 out of 100 isn't too uncommon to happen randomly, and that's 9%. And our threshold's usually 5% or less. So in this situation, I'd say no, it's not rigged. There's about a 9% chance of getting both winners from AP Stats in a fair lottery according to our simulation. Since this probability is not small and could easily occur by random chance, so in other words, it's more than 5%, we don't have convincing evidence that the lottery was unfair. So again, when we're looking for convincing evidence, we're looking for that percentage in our simulation to be so small to occur that random chance can't really explain it very well. All right, here's a check your understanding. Back to the Wheel of Fortune situation. Some people have wondered if Wheel of Fortune wheel is fair. If it is fair, the bankrupt result should occur with the probability of 1 out of 9. We talked about that earlier. To test the wheel, Pat Sajak, Ryan Seacrest now, observed a random sample of 50 spins of the wheel and found that bankrupt was spun 10 times. Is this convincing evidence that the bankrupt comes up more often than it should? So to answer that question, we don't just say 10 out of 50. Remember, 50 spins is one trial, and we have to do that many, many times. So how would we carry out this simulation to estimate the probability that in a fair wheel, bankrupt comes up 10 or more times? I would use a random number generator in this case. I tend to not use the table of digits. That seems to be too time consuming. So a random number generator. Here's what I'm going to do. First, I'm going to let 1 equal bankrupt and 2 through 9 equal not bankrupt, since we want to mimic this 1 and 9. So 1 is bankrupt, 2 through 9 not bankrupt. We're going to use a random number generator to select 50 integers between 1 and 9. We're going to count the number of ones, since I've designated ones as bankrupts, in those 50 spins. And we're going to do this many, many times. Let me show you on a calculator how I would do that. To do this on a calculator, we're going to go to math again. We're going to go to prob. And we're going to go to randint. And once again, we can have the same number repeated. So if we get bankrupt 5 times in a row, then you get 5 ones. In this case here, I want to do 50 spins. So I'm going to have my n be 5, but my numbers are going to be 1 through 9. And remember, I designated 1 to be bankrupt. So anytime I see the number 1, that's considered a bankrupt. I'd hit that 50 times. I'd press paste, press enter. And I'd go through and I'd count how many of those were ones. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of my 50 spins, wow, how lucky is that? Were bankrupt here in my one trial in my simulation. I would do this many, many times. So in class, we'll do a simulation together to kind of see what it would look like as a dot plot. Here's an example. So the dot plot is going to display the results of 100 simulated trials of 50 spins in a fair wheel. Explain what the 1 dot above 12 indicates. So again, this is what this represents here is 1 simulation of 50 spins. And of those 50 spins, 12 landed on bankrupt. That's what that means. What conclusion are we going to draw about 10 or more bankrupts spins occurring in 50 spins? So if you look over here, we have 100 dots. How many of those 100 dots had 10 or more bankrupts? Well, it's 4. So that's a 4% chance of that happening by random chance, assuming that the wheel's fair and the 1/9 probability is true. So we would say there's a 4 in 100 or 4% chance that 10 or more bankrupt occur in 100 trials of 50 spins, assuming the probability is actually 1/9 of getting bankrupt. Since that probability is so small, less than 5%, it's unlikely to happen by random chance. Therefore, we have convincing evidence that bankrupt comes up more often than it should. So you see the idea here, and this is an informal way to do inference. We'll have ways later in our course to do that without doing a simulation, but for right now, we don't know the math behind that. So a simulation with probability results can work as well. So just a couple things about simulations. We can do a coin flip for easy 50-50 chances. We can roll dice for 1 out of 6 chances. My favorite, of course, is the random number generator. That's the one you'll probably use the most often. I really don't like the table of random digits, if I'm being honest, but it comes up on some of your questions, so I do have to teach you how to do it. But it's just not my preferred way to do things for lots of trials. So let's do a lesson summary. First, random process is just generally describes the outcomes determined purely by chance. In the short run, things are unpredictable, where in the long run, they are predictable. So we always want to do many, many trials. The probability is that relative frequency in the long run of those many, many trials. It's always going to be between 0 and 1, or 0% and 100%. The law of large numbers describes that long run chance. In many, many trials, a random process will approach its theoretical probability, what we think it should be. And then finally, in a simulation, we want to describe how to set up and use a random process to perform one trial, identify what you're going to record at the end of the trial, do many of those trials, and answer the question. Use the results to answer whatever question of interest. Well, I do appreciate you watching this. Hopefully this helps you. In future videos, we're going to learn more formal ways to calculate probabilities, but this is a good kind of introduction to it. So thank you again for watching and have a great night.